Topic 4.1, we start with oscillations. This is the only equation in your data booklet on page 6. Period, which is capital T, equals 1 over F, F being the frequency. Oscillations are vibrations which repeat themselves, or they could be cycles. So an oscillation is the full extension of a spring followed by the reset of the spring. It's an up and down motion for a spring. We have a pendulum. Back and forth would be one oscillation or one cycle for the pendulum, all the way down, all the way back. Has to come to start. Or the vibrations on a stringed instrument. So a string has these oscillations back and forth, back and forth. Just so you know, in all oscillations at the maximum displacement from equilibrium, from the middle point, the velocity is 0. At the middle of the motion, you have maximum velocity. The max value of a displacement x naught is called amplitude. For this example, I have a spring with a mass resting on it, and you can see there's some middle line right there. That this midline right here is where the spring would be resting if it had not been displaced. This is called the equilibrium position, and the spring is oscillating with an amplitude of 4 meters. X naught, again, is the amplitude. The point where the displacement is 0 is the equilibrium position. Displacement, X naught, is always measured from equilibrium. You can combine waves. You can superimpose waves or overlap waves, and when you do, when waves combine, the displacements sum and not just the amplitudes. Again, amplitude is just the maximum displacement, but no matter how the waves are overlapped, you can find a sum for these waves, and you always add up their displacements, not just the amplitudes. What you're seeing here are green and blue waves moving with respect to one another, and as they're moving with respect to one another, you get this resulting red wave, which is an overlap of the two waves. So we can't describe oscillations without discussing the time nature of oscillations. So the time it takes an oscillator to complete a cycle, a down and back motion for a pendulum, an up and down motion of an oscillating spring, maybe the revolution of the Earth around the sun, this takes a certain amount of time, and this is known as the period of an oscillation. The SI unit for period or time is in seconds. On the other side, the flip side, we have frequency. So the frequency is the number of cycles, the number of oscillations, the number of down and back motions, up and down motions completed in 1 second. So period and frequency are inverses of each other. The SI unit for frequency is the inverse second, the reciprocal second, or hertz, named after the guy who discovered radio waves. So you can see on the right-hand side, we have 3 buttons that are flashing. The top button, this one up here, we have this on and off switch. This light is turning on and off once every 2 seconds, which means it has a frequency of 0.5 hertz. It takes longer for a cycle to be completed, so it has a low frequency. The middle one oscillates on and off every second. 1 divided by 1 is 1 second. So this, we will see this complete an on and off a total of once per second. That's its frequency. And here we have a button, the third button. It has the highest frequency because it flashes on and off in 5 seconds. So 1 divided by 0.5 seconds gives us 2 hertz. It has the shortest period, so it only takes 0.5 seconds to complete an on and off signal, and it has the highest frequency because it has the shortest period. We need to talk about equilibrium for an oscillator because I've discussed the equilibrium position for a spring. It's at a place of, it's at 0 displacement. Equilibrium really means the net force or torque on an object is 0. You can have equilibrium for an oscillating spring. That is a location where the net force acting on the spring is 0. Now look at this oscillator. This is a pendulum. You'll see that as it oscillates, the velocity and the acceleration are out of phase with each other. So velocity is 0 at its maximum displacements, at its amplitudes. The acceleration always guides the pendulum back towards this, which we would call the equilibrium position. This is where the pendulum would rest if it wasn't oscillating. Notice what happens, though, to the acceleration vector. When the pendulum is at its equilibrium position, the acceleration vector points straight up. We'll discuss why that is. A pendulum has an equilibrium position. This is the lowest point on the pendulum's trajectory, and it's along this line. It's where the angle would be 0 with respect to this yellow line. But it's important to know that this does not mean that there is no net force on the pendulum as it's passing through its equilibrium position. The swinging pendulum is never in equilibrium, even when it passes through its quote-unquote equilibrium position, because a swinging pendulum always has a net force acting on it. It's that center-seeking force. So at any point on the trajectory, there is always a net force, F net, the center-seeking force, which is the centripetal force. What guides the pendulum back and forth is a component of the force of gravity. So it's one component of Fg that guides the pendulum back and forth. But even at its equilibrium position, there is always a net force acting on a swinging pendulum. So a swinging pendulum is never in equilibrium. We discussed simple harmonic motion or simple harmonic oscillations. These are just very special types of oscillations in which an oscillator always returns to the same amplitude. In simple harmonic motion, the acceleration acting on the object is in the opposite direction to the object's displacement. Namely, acceleration is proportional to negative x. Any force that is proportional to the opposite of a displacement is called a restoring force. For any restoring force, F is proportional to negative x because A times m is F. Yes, we see since F equals ma, ma is proportional to negative x, or A is proportional to negative x. All restoring forces can drive simple harmonic motion. You pull on a spring, the spring tries to pull in the opposite direction. You displace a pendulum one way, let it go, it swings in the opposite direction of the displacement. Always, always, there is a phase difference between acceleration and displacement for a simple harmonic oscillator. So we can plot the displacement versus time for a spring. A spring is a simple harmonic oscillator in this case. We haven't deformed the spring. So the spring oscillates up and down. And as it does, I can run ticker tape out, and we could see over time the variation of the spring's displacement. Looks like a wave. So to know how many cycles it has completed or how to represent a single cycle on a graph, one cycle, one complete wave follows a 3-2 rule, always 3-2 rule. There are always 3 nodes and 2 crests. So a node is a place of 0 displacement, 0 amplitude. Right here is a node, node, node. And I can see this is a negative cosine wave, but this would be one cycle. Notice I have 2 nodes here and 1, 2, 3 crests, or antinodes for a standing wave. But for just a traveling wave, 3 crests, 2 nodes make up one cycle or one complete wave. If I start here at this position, we can see I can have 3 nodes, 1, 2, 3 nodes, and 2 crests. So one complete cycle, one complete wave follows a 3-2 rule, where you have 3 crests, 2 nodes, or 3 nodes, 2 crests. This looks like a sine wave right here, and this is more of a cosine wave. It's a negative cosine wave, but this would be a cosine wave. So for a spring, I can start oscillating it by fully stretching it, or I can completely compress it. both of the motions, once released, will have the same period, the same frequency of oscillation if it's the same spring with the same spring constant. But what changes is the phase difference, the phase of these cycles. These two will be out of phase by half of the period, or half of the cycle. They're going in totally opposite directions. All right, practice number 1. The graph shows measurements of the height h of sea level at different times t in the Bay of Fundy. What are the approximate amplitude and period of the waves? So you may be tempted to say, okay, the amplitude has to be from the very top to the very bottom, but this would not be correct. The amplitude is a measure of the height of half of the total wave height. So I'll draw a line bisecting the wave. So it's about right here. Oops, I'm trying to keep it straight. Maybe a little lower. I can see that the total height is around 13. And so waves are made up of crests that go above the nodal line and troughs that go below. So the amplitude is actually measured here to here and here to here. So the amplitude would be approximately 6.5 meters. It's just half of the total height that you see. And then it asks what is the approximate period. So remember the 3-2 rule. You have 1, 2, 3 crests and 2 nodes, or 2 crests and 3 nodes. In this case, I'm just going with a 3, 2, and so for an oscillation, it's an up, it's a down, and a back up, and that takes about, I don't know, 12.5 hours, or maybe about 12 hours. So the period, capital T, is about 12 hours. A buoy is floating at sea. If the buoy oscillates with a frequency of 0.4 Hertz and an amplitude of 0.80 meters, how long does it take for the buoy to move a vertical distance of 16 meters? Give your answer in seconds. So if you look at this GIF, you can see like water waves, and they're moving from left to right in this direction. But if you focus on this little yellow dot, pretend like that's our buoy. And the buoy itself doesn't oscillate with the wave. It doesn't continue to travel in this direction. Instead, it's really oscillating up and then down. And then it comes up and then down. Just watch the wave for a moment, or watch the buoy for a moment, and you can see that indeed the buoy itself is oscillating up and down. So if I were to sketch this wave, and I sketch it like the previous example, you know, the wave has a crest, crest, trough, and you know that you should bisect this wave to make your 2 nodes. Really should be higher bisection. It's fine. Okay, so the buoy in one oscillation is going to go down 0.8 meters if it starts at the top of the wave, then down further 0.8 meters, and then it's going to come back up back up 0.8 meters, and then to return to its original height, it needs to go a further 0.8 meters because the amplitude is just 0.8 meters. So in one oscillation, it travels the length of its amplitude, the length of the amplitude of the wave 4 times. That's in one oscillation. So one oscillation, the buoy travels 4 times the amplitude of the wave. So 4 times 0.8 is 3.2 meters. The question asks, how long does it take for the buoy to move a vertical distance of 16 meters? So let's see how many oscillations the buoy would have to go through to travel 16 meters. So to figure out the number of oscillations, I'll do 16 meters, and I can divide by 3.2 meters, and this gives me an answer of 5 meters. So again, I took the total vertical distance traveled by the buoy in a single oscillation, and I divided that from this 16 meters, and that gives me 5 oscillations that the buoy has to go through in order to travel a total distance of 16 meters. Okay, so 5 oscillations. The buoy has a frequency of 0.4 hertz. So what's the period of these oscillations? Well, period and frequency are inverses of each other. So to get the period, I can do 1 over 0.4. And 1 over 0.4 is, what's that, 2.5? 1 second, brain fart. Yes, it is 2.5. Oh my God. 2.5 seconds is the period of an oscillation, and the buoy is going to go through 5 of these. So if I just multiply this by 5, I can see that the total time it takes for the buoy to travel a vertical distance of 16 meters is 12.5 seconds. 12.5 seconds. Hopefully you all can see that. That's the total time. Finally, practice 3. For an object experiencing simple harmonic motion, sketch a graph of its acceleration versus displacement. It's very easy. Sketch your axes here. Acceleration is on the y-axis, displacement is on the x-axis. And these are always opposites of each other. So you will have a straight line passing through the origin with a negative slope. And this shows that the acceleration is proportional to the opposite of the displacement vector. All right, thanks for watching. Study well.